There's an easy way to work with calculating buffer concentrations called the Henderson-Hasselbalch equation. And really all it is, write out Ka. Okay, so I've got our Ka that expresses a relationship between H3O plus, the conjugate base concentration, and the original acid concentration. So let's take the log of both sides. Take the log 10 of both sides. Log 10 Ka equals, and now we can just write this, a log of a product becomes the sum of a log. So this is log 10 H3O plus log 10 of A minus over HA. And we'll keep that ratio there. Well, multiplied by -1 on both sides. And what we have then is the pKa is equal to the pH minus log 10 of the ratio of A minus and HA. Let's rearrange this a little and we get the pH is equal to pKa plus log 10 of the ratio of the conjugate base to its acid. So this is really nice. If we have the pKa's tabulated and we know how much of acid and base there is, we know the pH. So this is so simple, it's actually interesting. They named it after two different people. You'd think you wouldn't need two people to come up with this, but here we are. So Henderson-Hasselbalch equation. Okay, so let's see what happens if we have a bad buffer. Let's see it now that we've got an equation to work with this. Let's see what happens in a bad buffer. So we're going to start out with a 3.6 times 10 to the minus fifth solution of hydrochloric acid. It has a pH of 4.44. What's the pH change when an equal volume of 0.01 molar sodium hydroxide is added to the system? So let's see. So our initial concentration of H plus is 3.6 times 10 to the minus 5. And then we double the volume. That takes us down to 1.8 times 10 to the minus 5 molar. Our OH minus concentration, that's 0.01 molar. It's equal volumes. That takes us down, because we're pouring the two volumes together, 0.5 molar. And then they react with each other. But then when they react with each other, then essentially the H plus goes to 0. And the OH minus, it's 0.005 minus 0.00002. That's 0.00498. We only have two significant digits. So we have our final OH minus is just going to be 0.005 molar. And so our POH is minus log 10, 0.0050. And that is 2.30. So the pH is 14 minus 0.30, 2. 14 minus 2.30 equals 11.7. So our change in pH is 11.7 minus 4.44. That was the initial concentration, 7.26. This is not a good buffer. It's hydrochloric acid at a relatively high pH for an acid. But if you add any base, you get a huge pH change. It immediately becomes extremely basic. So that is not a good buffer. Now let's look at something that supposedly is a good buffer. Our example of acetic acid and sodium acetate. And the pH is exactly the same in this case. A solution containing 0.10 molar acetic acid and 0.05 molar sodium acetate. Okay, so now one thing you notice here, there's actually no Ka, but that's okay. We can calculate it, right? We have enough information to calculate. Ka equals H plus times A minus over HA. Well, that's just going to be equal to 10 to the minus 4.44, 0.05, and 0.10. And so that equals 1.8 times 10 to the minus 5, which is not surprising if you remember that Ka from other places. So, what is the concentration of A minus and HA going to be now? Well, originally we had 0.1 mole of HA, but we're adding we're adding 0.01. Now, notice that we don't say how much total there is. Let's just assume 1 liter. So that means we, I guess, made that assumption already, that we have 0.1 mole HA, and then we add 0.01 mole of NaOH. And so that means that's going to react with 0.1 minus 0.01 to produce 0.09 moles of HA, right? Because the strong acid is going to react completely. The strong base is going to react completely with the weak acid. And so they'll react until all of the 0.01 moles of NaOH is used up. We'll get 0.09 moles of weak acid. Conversely, we have 0.05 moles of the conjugate base. And so we get 0.05 plus 0.01 because all of that acid that reacts is going to be converted to conjugate base. So we get 0.06 mole A minus. Okay, great. So now we can just say that the new pH is going to be the pKa. So if this is the Ka, then the pKa is 4.74 just by taking minus log 10. pKa plus log 10 of, now this is important, remember the directions. It's 0, which goes on where? The conjugate base goes on top and the acid goes on the bottom. And that is equal to simply the pH, it's 4.74 minus plus log 10, 0.06, 0.09, and that equals 4.57. And so the change in pH is just going to be 4.57 minus 4.44 equals 0.13. So this is a good buffer. We added a lot of sodium hydroxide and it barely changed the pH at all. It did get a little higher as we'd expect it to. We're adding base, but it didn't get very much higher. This makes sense here. It should be a little bit lower than the pKa because in this buffer, there's a little bit more acid than there is conjugate base, and therefore the pH will be a little bit lower than the pKa would be. Okay, so we've seen what a good buffer can do. Let's use Henderson-Hasselbalch and yes, oh yeah. Do I need to worry about X is small? This is a point that's raised in the book. And so this is the Ka. So when do you need to worry about whether X is small? So first you have to ask, are the concentration of acid and the concentration of conjugate base, are those the initial concentrations or the equilibrium concentrations? When you say, I have a solution that has this much acid and then has this much base, then those are the equilibrium concentrations. And there's really no, there's no approximation there. That is the concentration of equilibrium. So Henderson-Hasselbalch is exact if the concentration of HA and A minus are the equilibrium concentrations. If they're initial concentrations, then you would need to see, okay, at equilibrium, I added this amount of acid and conjugate base, what's going to happen? What equilibrium is going to be reached? So you need to solve something like this, that the Ka is equal to A minus initial plus X, times the amount of H there plus created, divided by HA initial minus X. However, if the concentrations are fairly large, 0.1 molar or larger, and the acid is weak, then the small x approximation is almost always good. Why? Because, assuming these are about equal, then these will more or less cancel out and Ka will be roughly equal to x. I mean, it might be 2 times Ka or half of Ka, but that's as long as Ka is small compared to this, then that it's generally a good approximation to assume that it's small. So, so that's the thing. You generally don't need to worry about it. If you have very dilute concentrations, then you would need to go and check this more carefully. Of course, if you have very dilute concentrations, you really don't have a buffer. So you probably wouldn't be using this equation anyway.